So, before I get started, one announcement. Please remember that Professor Seidel has a class in here before us. I think only on Tuesdays, I'm not sure if it's both days. And some folks are coming a little bit early and disrupting the class. So please be respectful, but don't come in until 9:20, okay? Thank you. All right, very good. So let's see. So the current problem set is a 2-week assignment due not Thursday, but a week from then. I modified slightly problem one so that there's sort of, you know, what you're, show that so you know what you're trying to get to. And so you can download a fresh copy. Our first exam. So you have ChatGPT to thank for this. I kind of played around and said, no, it's not, you can't give a take-home exam anymore. There's just no way. There's just too much information out there. Yeah.
I asked ChatGPT a question that might be on our exam and it gave you anything reasonable?
It did. Just maybe those problems are too easy. But yeah, it's kind of amazing. That wasn't ChatGPT, but it's another much more powerful thing. So in any event, the exam will be in class. It will be on March 4th. We'll talk more about it as the time approaches. You know, my main thing is that I don't want the time to be the major issue. I know it will be, because, you know, not the major issue, but it will be an issue because that's life. There's time and time is finite quantity. In any event, we'll cross that bridge, okay? Good, all right, we took a deep breath and we're moving on. So, we started talking about the last lecture, and will be the subject of this week's lectures, is the very, very important subject of multipole moments, okay? So, I just wanted to again, to sort of motivate and set the stage for this. The notion of moments of a distribution is a notion that should be familiar from the perspective of statistics, okay? So if we have a probability distribution and a probability density function over, say, one variable, we can talk about the moments of that distribution, right? And so, excuse me, I should say x to the power n. That's the nth order moment, so when x is 1, that's the mean value. X squared tells us something about the variance, right? The difference between the mean value and its average, how that's distributed, of course, which is equal to the difference in those guys. You know, is an important quantity that tells us something about how the weight of the distribution is distributed around the mean, okay? So importantly, if you know all the moments, you know the distribution, okay? So the moments define the distribution. They're properties of the distribution. And we can think about that for a joint probability distribution associated with multiple variables. We would have some, for example, in this case, monomial in those guys, or that tells us what that particular moment is associated with those different variables, right? So that's the concept that I hope you've seen in thinking about probability distributions. It sort of sets the stage for what multipole moments are in electrostatics, particularly, say. We'll also talk about them magnetostatics and in dynamics. So the moments are a property of the charge distribution. In this case, the charge distribution is the charge density rho, okay? And if we know what the moments are, then we can write a good approximation to what the potential is. In fact, we can write a power series that determines what the electrostatic potential is far from where the distribution is localized, okay? So the problem at hand is one in which we have some charge distribution, and we are looking at it at some distance that's far compared to all the points. So here's the origin. This is my charge distribution. We're looking at the charge distribution at the points x prime and its contribution to the potential at the point of observation. Right, so our goal is to calculate this. Now we know if there's no other boundaries and no other charges and no other things, we have an exact expression for this in terms of the simple Green's function, which is just Coulomb's law. And our goal is to write a power series expansion in the case that the distance from the origin is huge compared to any place that the charge is relative to the origin, okay? So the charge distribution is localized in some region, and we're far away from it. And we just want to do a Taylor series expansion. That's just what we want to do. It's complicated. It gets messy. This gets really messy. But we're going to try to step through this together, okay? So to do that, I just want to remind you of some things about power series, okay? So if I have some function, and I want to look at a power series expansion of this where A is small. Well, let me call it epsilon, just so that, we'll emphasize the fact that this is much, much less than 1. Well, then we can write this as a power series, right? So to lowest order, it's this, and then we have a first order correction, which is this, and we have the second order correction, which is this. That's dot, 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 1 over n factorial, epsilon to the nth derivative of this, right? All as at x. So that's an expression of Taylor series, okay? Just to remind you of something, you can think about this Taylor series expansion in a kind of formal way. As that, does that, right? If I were to take, this is an operator in the exponent, but we know how to do that. You do that in quantum mechanics all the time. And if I were to write this as a power series, right? That's epsilon to the n over n factorial acting on that. And so this is why the derivative is the generator of displacements in x. That's why the momentum operator, which generates displacements, is the derivative operator, right? This is just e to the minus I, epsilon times the momentum operator. The i's cancel, and this is where that comes from if no one ever taught you that, Yeah,
Where the road is non-negligible?
Yeah,
or-
that's what I think. Yeah, where it's not zero.
Oh, okay.
Yeah, or close to zero, yeah. Okay, so if I had a multi-valued function, like a function of x, y, and z, right, then I could write this as either the this is the three-dimensional version of it, of this, which is f of x plus epsilon dotted into that plus a half epsilon dot epsilon acting on epsilon dot epsilon, which is epsilon I, epsilon j plus dot dot dot. Nice. So what we are looking to do in creating this power series is essentially write a power series expansion for the Green's function, where x prime, its magnitude is very small compared to x, so x prime is playing the role of the small displacement. So what this tells me yeah. We're going to come back to that expression. That's a kind of fancy schmancy way of writing the Taylor series expansion. We're going to come back to that in a moment. Let's do it a little bit more sort of brute force to start. Okay? So let's write this, which is equal to the square root of the vector dotted into itself, which is equal to 1 over the, let's write it this way, r squared minus 2 r prime, r hat, that r hat prime, plus r prime squared to the 1/2, where I've written x having a magnitude r and a direction r hat, and x prime as having a magnitude r prime and a direction r hat prime. Okay? So these are unit vectors along the direction x and along the direction r. And we're looking at the small parameter here, epsilon, is that we want to have the magnitude, which is r prime, much smaller than r. Okay? So how would you Taylor series expand that? What's the first step? The first step is to write everything in terms of the small parameter. That's the first step. Which means if this is a small parameter, I have to factor out an r squared so that everything is in terms of the ratio of r prime over r. Okay? So I get a 1 over r, and then I get 1 minus 2 r prime over r. I'm going to call this then cosine gamma plus r prime over r to the power 2, all of the square root, where I've just defined this as the angle between those two unit vectors. Okay, so those two unit vectors have that angle. Yeah? That should be to the minus 1. You with me? Okay. Now what?
You get in terms of displacement.
I could, but I'm going to be simple-minded here. I have something to a power, and I want to do a Taylor series expansion. I use a binomial theorem. That's the first thing I do, right? And so the binomial theorem, which is just what the Taylor series expansion is, if I have 1 plus a small quantity to a power n is equal to what? Well, it's approximately 1 plus n times epsilon to lowest order, and then there's the quadratic corrections, which is y. 1/2 n times n minus 1 epsilon squared plus something of order epsilon cubed. Okay? So that means that when n is minus, hold on a second. Yeah, that's right. So when n is equal to minus 1/2, this is equal to 1 minus 1/2 times epsilon, and then I get, when I get n times n minus 1/2 is plus 3/8 epsilon squared. Okay,
I haven't actually plugged in our thing yet at all.
this is just a reminder of the binomial theorem, and now I want to use that here. Okay, so what does that tell me now in terms of the Green's function? Well, the lowest order, so this is going to, I'm going to call this thing, now you have it in your notes, so I can erase it and be a bad professor. So I want to expand this to order epsilon squared. It could continue to epsilon cubed, but that gets really tedious. So how would I do it? Well, I use this formula, okay? So the lowest order term is equal to, so I have 1 over r, so I get, the lowest order term is 1. And then I get plus this thing to the power, which is plus epsilon cosine gamma minus 1/2 epsilon squared. That's from the first order term. But then I have to take the quadratic term, right? The quadratic term over here is coming from this, because if I do this squared, I get that to the power 4. So I get plus 3/8 minus 2 epsilon cosine theta
Won't that be minus?
squared. Excuse me? I have plus 3/8.
Yeah, you put minus instead.
I just squared it, yeah.
Where did the factor of 2 in front of the epsilon go?
Oh, yeah, that's right. This guy went away because I had a 2 epsilon. I multiplied that by minus 1/2.
Okay.
Right?
Okay.
Which is what I have over here.
I see.
Okay. So this is this plus order epsilon cubed. Let's double check my algebra with the answer key. Very good. All right, so let's put that all together. And what we have then is that the Green's function is equal to lowest order, 1 over r, and let's just plug in all that stuff. cosine theta, or there's that. I'll put back in our number, that's the first term that we had. And then when I square all that out, I get the following. That's correct. Okay. So let's continue to multiply things out over here. And I get the following. The first term is 1 over r. The second term is equal to, let's say I want to write this. I have r hat over r cubed, and then dotted into x prime. X prime is a vector whose magnitude is this and direction is that. Okay, so that's the first term. I've written that back out. And now I'm going to be very tricky. Let's just, as a little aside over here, I'm going to write this as r hat dot r prime dot r hat. That's fine. I can write it in any order I like. But you notice that this is an outer product. This is a dyadic. And then I've dotted it with vectors. Everyone loves the outer product. That's what it is. All right? So this is then equal to the following thing. And 1 is r hat dotted into the identity dotted into r hat. So I can factor out the r hats on both sides, and I get the following. I get 1/2. I get, there's an r squared in the denominator and an r over here, so that's a 1 over r cubed. And then I get r hat dotted into the tensor. The outer product of x prime with itself minus r prime squared times the identity dotted into r hat plus order r prime over r cubed. Okay, this is a little bit of a complicated expression, so let's look at it together. So the dominant term, when x prime is tiny compared to x, is that I just ignore x prime altogether, and this just is 1 over r, okay? That's the dominant term here, okay? But there are corrections. The first term is linear in x prime, and it's the vector x prime dotted into this vector. Okay. More importantly, this term goes like 1 over r. This term goes like 1 over r squared. And then the next term, which is quadratic in the size of x prime, goes like 1 over r cubed. And it itself is defined not by the vector x prime, but by this tensor. Okay? It's a rank 2 tensor. And it's a function of where the charges are. Okay? So this is an expression that we can now use to plug back in here, and in doing so, we get the multipole expansion, at least up to second order. Yeah?
So I understand how this gets us 1 over x minus x prime, but where in this process did we actually take a power series?
Right here.
That's when we did the binomial.
That is a power
That,
series.
okay, that was the instance of us using the power.
Yeah, this is a power series. This is the Taylor expansion of this function when epsilon is small. The binomial expansion is just an example of a power series, one that we know or we should just know without taking the derivatives and plugging it in. We just memorize it because there are some things we know, and this is one of them. I say we know it because I demand it. Okay, so one of the things that you will know is the binomial expansion to second order, and you'll never have to write this power series by hand again. You just know it. So that's where we did it. Okay, so excellent. So now, given this expansion, which is to order, second order in the ratio of r prime to r, we can plug this in to phi, and we get the following expression. This is the multipole expansion. Where if we plug that in, Q net is equal to that. So when I plug that expression back into that, I'm going to get an integral over rho, right? Everyone see that? When I plug that back in to this, the first thing is going to be integral over rho. P is equal to, I'll just emphasize that I'm integrating over x prime. This is the monopole moment. I told you we'd talk about electric monopoles.
I appreciate it.
This is the electric dipole moment, which is a vector. And then we have this crazy devil with this two-horn Q, capital Q, which is the integral over the charge distribution 3x outer product of x prime with x minus r prime squared times the identity tensor. I should write it that way. Sort of a hat, excuse me. It needs to have its devil horns. And this is the quadrupole moment tensor. Okay? Let's pause for a moment to try to understand what the hell we're talking about here. So, does everyone understand how I got from this expression to this expression? What I did is I plugged the Green's function back into here, and I factored out everything that didn't depend on x prime, because they can come outside by writing the Green's function in this way. This stuff depends on x prime, and this stuff depends on x prime. And it stays in the integral. And everything that doesn't depend on x prime came outside the integral. And I got this. Everyone clear on that or have a question about that? Yeah.
So we took that in the expansion of the multiple expansion. those halves, are they supposed to be vector position or unit vectors?
Which ones?
The halves between like at the quadruple moment.
I think those are unit vectors.
These guys are unit vectors. These guys are unit vectors. These guys were unit vectors, but they got multiplied by r, the magnitude. And then they became the vector x prime. But these are the unit vectors. Yeah, thank you. So, what we have, notice, these guys are moments of the distribution in the same spirit as we had in the introduction to this lecture, okay? This thing is a kind of normalization. What is this? This is the total net charge of the system. It's the total net charge. Integrated over space. If it was neutral, this would be 0, but if it has some net charge, it will be either positive or negative. And what this says is that if I'm far away from the distribution, over here, and this thing has some charge, I could just treat it as a point charge at the origin, right? This is the potential of a point charge at the origin. And so it's the dominant term. If this thing has any net charge at all, if I'm far away and r is big, these other terms will be negligible and it will be dominated by the monopole term. However, if the net charge is 0, say for example I have equal and opposite point charges, then, or have an atom, right, which has a neutral atom which has equal number of protons to electrons, then the charge distribution is neutral and there is no net charge. And the dominant term will be this one, which falls off faster, falls off like 1 over r squared, and its potential is determined by this vector, which is saying something about like average position of the charges, right? It's like the one, right? And then finally, we have another correction, which is more complicated, which is this dude, the quadrupole tensor. And just, again, this guy has components. So this is a tensor whose components are this. They're of the same spirit as what I was saying over here when we talked about moments of, a joint probability distribution. In this case, this is a polynomial in the components x, y, and z. And when I weight these particular components and average them over the charge density, I get the components of the quadrupole. We'll give them a physical meaning in a moment. Yeah.
So earlier you said you got these by plugging that expression after we did the binomial expansion into the integral and factoring out stuff that depends on x.
Yeah.
But can't r be written in terms of x?
No, all the things that don't depend on x prime.
That don't, okay.
So if you look at the first, so let's just for the heck of it, let me just show you. If I plugged in this guy and I integrated this term with respect to the charge distribution, right? That's one of the terms. I can factor this outside the integral because it doesn't depend on x prime.
Okay.
Because I'm integrating over the charge distribution.
Okay. But then we still have the x prime integral.
We do.
Yeah.
And that is exactly what I just wrote down.
Those are the monopole,
There it
dipole,
is.
and quadrupole moment. I see. Okay.
The integral over the stuff is the moment.
I see.
That is the moment.
That clears it up.
Yeah,
Thank you.
thank you. Great. Okay. So let's try to unpack this a little bit and talk about the sort of physical meaning of these things. Okay. So again, I just for clarity here, let me write the matrix here, matrix representation of this as a 3x3 matrix. Okay. So if I look at this, remember R squared is x prime squared plus y prime squared plus z prime squared. Okay. So what I get if I were to write this out as a matrix is that this would be equal to 2x squared minus y squared minus z squared under the diagonal, 3xy and 3xz. Then on the next diagonal I get 2y squared minus x squared minus z squared, 3yz, and then 2z squared minus x squared minus y squared. And then notice that this is symmetric. So that this, I only need to write one of the orthogonals because this guy is equal to the same thing.
Where did the primes go?
What am I doing here? This is an integral, I'm sorry. Yeah, what I wrote is not, this is an integral over this rho x. Now, at this point, it's a dummy variable. Who needs no stinking primes? Because I'm not keeping track of them. I could put everything a prime, but why would you bother? You've gotten rid, inside the integral, I can choose it to be anything I want, okay? But there are a couple of points I want to emphasize here, which is that this tensor is symmetric. So this is 3yx, but y and x doesn't matter what order I write them in, it's the same thing. So this guy is 3yz, and this guy is 3xz. So I only need to worry about these components. These components are determined by the off-diagonals because they're equal, because it's a symmetric tensor. The off-diagonal elements are, yeah?
So for some charge distribution,
Yep.
these x, y's, and z's are just sort of dummy variables we're integrating over.
Yeah, they are the positions of the charges.
And then for discrete, it would just be the magnitude of like where they are.
It would be the sum of their x. So instead of having an integral, we would sum over this, where these are the x, y, and z coordinates of that particular charge. And then we have to square it. Okay, so moreover, if I look at the trace of this tensor, which is the sum of its diagonal elements, it's the trace of this, which means set I equal to j, and sum over repeated indices. Okay. So let's just ask ourselves, what is the trace of 3xi xj minus r squared delta ij? What is the trace of that tensor? Well, it's 3xi xi minus r squared, and what's the trace of this? 3. This is the identity matrix, got 1, 1, 1. But what is xi xi? That's r squared, right? Because it's the sum of x squared plus y squared plus z squared, which is r squared. So this is 0, okay? So the trace of the quadrupole tensor is 0. and it's symmetric. Let's say the off-diagonal elements are equal. Such a tensor, as we studied in the first problem set, is what we call an irreducible tensor. There was method to my madness as to why we started there, because this is an important concept that will be particularly important in thinking about multipole moments. So the quadruple tensor is an irreducible rank 2 tensor. And how many independent components are there? How many numbers do I need to specify the full tensor? Well, I don't need to specify the off, right? I only have half the off diagonal. And also, if I have 2 of these diagonal elements, I know the third one because it has to be the negative of the sum of the other 2. So given that, how many elements are there? 5. We'll come back to that, why that number matters. That number is equal to 2 times 2 plus 1. Well, it actually means something. It actually means something. We'll explain why that is actually the right way to think about 5 in this context.
It's also equal to 5 times 1.
Yeah, but that's meaningless.
Yeah.
This means something. You'll see why. All right, so let's think about now these guys, our friends. The monopole, the electric dipole, and the electric quadrupole. And let's try to understand a little bit better what they mean. Well, the monopole is obvious. It's the net charge. And we just described how if I have a certain net charge. The other ones are relatively straightforward, but let's just talk about it. So let's suppose we write the charge density I don't want that. I want to make sure these are here. Let's see, where are they? So the guy can look at. Okay, those are the things we want to look at. So let's write the charge density. Let's separate out the amount, the positive charge distribution and the negative charge distribution. I've normalized this such that this is a 3D probability distribution, either the plus or the minus. Okay? I'm defining n as the distribution probability charge normalized to 1. Okay. So I can always say, here's the positive charge, integrate over it, that's the total positive charge, divide by that, and you get it, right? So what this tells me is the following: Q, the net charge, which is the total integral over rho, is equal to Q plus the integral of this. No, I'm going to write this as minus, where Q minus, so I can find it in this way, such that this is equal to Q plus Q minus. So Q plus equals the magnitude of positive charge in the distribution, and Q minus is the magnitude of negative charge. Is that clear? So the net charge is the difference between the amount of positive charge and the amount of negative charge. Okay? What about the dipole vector? The dipole moment vector, I integrate over the positions weighted by the charge density. Let's use this representation of it. So this is equal to the mean position of the positive charge, and this is equal to the mean position as a probability distribution of the negative charge. Right? In the same way that we thought about a probability distribution, think about n as the probability distribution of where the positive charges are. So the electric dipole moment is the magnitude of the positive charge times the mean position of the positive charge minus the amount of negative charge times the mean position vector of the negative charge. It's telling me how the positive and negative charges are separated from one another, okay? So for example, if I had two equal and opposite charges, such as the magnitude of Q plus was equal to the magnitude of Q minus, for example, if I had an electron and a proton, then there would be an electric dipole moment going from minus to plus, right? Because it's weighted in that way because of this minus sign. And the direction of the vector is the direction in which the positive charge is separated from the negative charge. And the magnitude of the vector depends on the amount of charge and the separation between them. That's the electric dipole vector, okay? What is the quadrupole telling you?
Two pluses, two minuses.
Yeah, so I could have something like that, and in that case I wouldn't have a dipole, for sure. So let's write out some stuff. Oh boy. Okay. Suppose we only have positive charge. Okay, just for the heck of it, just to get some intuition here. And so we'll just say, in this case, that rho of x is whatever the magnitude of the positive charge weighting some normalized distribution, okay? Which I can always do by integrating this over x and dividing by its magnitude, okay? So in this case, Q net is equal to Q plus, and to lowest order, the potential would be what? What's the dominant potential from far away? 1 over r times Q plus, right? It would just look like a point charge at the origin. Okay? Let's also suppose that this thing is centered at the origin. the dipole moment is 0. What's going to be the first order correction?
One over R squared.
Well, 1 over r squared would be true if it had a dipole moment.
So 0.
So what's the next correction? 1 over r cubed. The first order correction will go like 1 over r cubed, and it will be quadrupole,
Why is the dipole moment 0?
because the mean position is 0,
Oh,
right? So there's no separation. Yeah.
So the dipole moment depends on coordinate?
It depends on the origin. It will not depend on the origin if the net charge were 0, then the dipole moment only depends on the separation. It doesn't depend where the origin is. But if there is a net dipole moment, if I just have a single electron oscillating around the origin, the dipole moment is not 0. It has a mean dipole moment because it's changing relative to the origin. Yeah.
Why should we have a quadrupole moment if there's no dipole?
Well, that's good. I can have a dipole moment if there's no monopole moment. One doesn't depend on the other. I can have something which has a variance but a 0 mean.
Okay.
Right? So that's exactly the point. And look, it's a very good point. Let's see what happens. So let's take a look at what the quadrupole moment is. So the lowest order, the first order correction, because the dipole is 0, the first possible correction is quadrupole. Okay. So let's write down the quadrupole tensor for this distribution. I'm just plugging in plugging in rho into our definition of the quadrupole tensor. Okay. So first, let's look at the off-diagonal elements of this thing. Oh, okay, I know what I'm saying. Let's suppose that the distribution is spherically symmetric. About the origin. If it's spherically symmetric about the origin, well then this first point is clearly true. The mean position is it's centered at the origin, its mean position is 0. Well, what does that tell me about the quadrupole for spherically symmetric distributions? Okay. Let's take a look at, firstly, an off-diagonal component where I doesn't equal j. Okay, so that component will be equal to which only depends on r. It doesn't depend on the direction. Okay. So does everyone see how I got that? I'm looking at an off-diagonal component where I doesn't equal j. There's no contribution here, and I have this. What is this integral? If I doesn't equal j. Well, if I doesn't equal j, this is going to be either x or y or z, and there's not going to be x squared, there's not going to be any y squared, there's not going to be any z squared. So this is going to depend on theta or phi. But when I integrate those functions over theta and phi, they're gonna be 0, because it's spherically symmetric. So this is 0 if it's spherically symmetric, okay? Moreover, let's look at the diagonal elements of this guy. Let's look at, for example, of QXX. QXX is Q plus the integral over all space. XX means I get 3x squared minus r squared times this. Which only depends on r. Right? Which is equal to q plus times 3 times the moment, the magnitude of x squared minus r squared. Everyone with me? Right? That's what this moment is. However, this thing is spherically symmetric. So what's the difference between a distance x squared from the origin versus y squared versus the origin versus z squared from the origin? Nothing. I can't tell the difference, which means the mean of x squared has to equal the mean of y squared, has to equal the mean of z squared. Because it's spherically symmetric, who knows where the heck x, y, and z is? I can go any direction and they're the same. Therefore, this is equal to 1/3 the magnitude of r squared, because the magnitude of r squared is x squared plus y squared plus z squared, but they're all equal, right? So this is then equal to 1/3 r squared, and therefore this is 0, which means the whole quadrupole moment is 0. In fact, all of the moments other than the monopole moment will be 0 if I have a distribution which is spherically symmetric at the origin, which we kind of know from Gauss's law. Because we know from Gauss's law, if I look outside the charge distribution, it's as if there was a point charge at the origin. So if I have a distribution and it's spherically symmetric at the origin, and I look at some distance away, this just is equal to a point charge at the origin. And that's pure monopole. None of the other moments do anything at all. So what the quadrupole moment is kind of, one of the things it kind of tells us is how non-spherically symmetric the distribution is. One aspect of the quadrupole is how the distribution differs from a spherically symmetric distribution. It's kind of the variance relative to a sphere. Yeah.
So at the beginning of this process, we said, oh, let's only consider we have positive charges.
Yeah.
But if we had some negative charge as well, but it was still spherically symmetric, so like the distribution is still spherically symmetric in both positive and negative charge,
Yeah.
then we would still get a monopole?
If we would.
We
We
would.
would, unless it wasn't spherically symmetric.
Yeah.
So this is the Q net, which is equal to Q plus minus Q minus over R.
Mhm.
So even if we had some negative charge, if it was all spherically symmetric around the origin, it would only have a monopole.
Right.
Okay. Let's just check for an example that we did super quickly last lecture. Okay. Let's look at the problem of a burning ring of charge. Okay. And this ring of charge has a radius A, and it has a total charge Q around uniformly distributed on a line. That's a ring, okay? And I'm on the z-axis, just for the heck of it, because it's easy. And I'm looking down from above with my big fat eyeball at the z-axis. And I want to know what the potential is when I'm at a distance z that's huge compared to this ring. Okay, so to lowest order, what is the potential when z is much, much bigger than a?
1/r.
And in that case, r is what? Z. That's my position. And what's plus something potentially of order r cubed or z cubed? Because that's the quadrupole contribution. Now, did we see that? Yes, we did. Because if you remember, if I looked at this as strictly r, the exact potential every point on this ring is a distance 50r away from z. So the exact potential is that script r, where script r is a hypotenuse, which is z squared plus a squared. Right? And if we factored out that, that was equal to 1 plus a squared over z squared to the minus a half. Right?
Why are we neglecting the dipole moment here?
This is the exact potential. I'm not writing a multipole expansion at all.
Okay.
Now, that is a good question. We'll come back to, let me just do this expansion and we'll see. We're not neglecting anything. The dipole moment is 0. Let's explain why in a moment. This is an exact expression for the potential at this point. It's just the charge integrated over that. That's exactly that. Everyone see that? I've written that script r as the hypotenuse of that triangle. I then factored out that. Tell me what this is to order 1 over z cubed. Because you know the binomial expansion.
1.
I 1, and then I multiply this by the exponent. Okay. This is the quadrupole. On the z-axis, this is what it is. Outside the z-axis, it's more complicated. The first order correction is z cubed, 1 over z cubed. The dominant term was the monopole. Question. Answer Benny's question. What happened to the dipole term? Why didn't it have a 1 over z squared? Yeah.
All the dipoles canceled?
There, yeah, the dipole is 0 because what is the dipole? It's the mean position of the positive versus the mean position of the negative.
And if it's all positive, then this one cancels, yes.
So the mean position is 0. This guy has the dipole vector is exactly 0 in this, for this distribution. This distribution has no, but it has a quadrupole. And that quadrupole is expressing the fact that this is not a spherically symmetric distribution. And the fact that it's spread out along this direction is why it has this form. Okay? So the quadrupole, so for example, in your homework, you have an example where you have an expression for the nucleus, which has a charge distribution that's kind of an ellipsoid. And this, I'm sorry, we'll never see that again. Oops. Anyway, moving right along, we have this egg-shaped thing. The charge distribution of the nucleus of some big atoms is quadrupolar. And that is, I mean, I work with it all the time. Strontium-87 is my favorite atom these days, and it has a quadrupolar electric field, which affects its hyperfine structure. Yeah.
Will our poles always be powers of 2?
Yes, yes, so there's each one, because it's related to what Arika said, we can make it by creating canceling pairs of charges. So when you write down, as you will, if you choose to do so for extra credit, the equipotential surfaces, they have that 2 poles, 4 poles, 8 poles, octopoles, etc. Hexadecimal poles. Good. All right. Excellent. What's next? I forgot.
Do we use, Legendre, polynomials at all?
We will. We're going to get there very soon. Yep. So let's now. I'm going to. Oh yeah. Nice. Lost my tenure for that. What car? That might be up there. All right. So I want to come back to what we were talking about at the. Well, maybe I want to say maybe one other thing. Let me come back over here to these expressions that we had for. So given the moments, whether it be the monopole, the dipole, the quadrupole, I can write down the potential. So in the distance when I'm far away, it gives me the approximate expression. So so far away. For example, suppose we found we had a charge distribution. Suppose the dipole moment was some charge times some distance along the z-axis. What is the electrostatic potential as a function of position far away from the origin? What's the exact potential?
Q net over R?
No, it has no, let's say that Q net is 0. It's a pure, a dipole is the dominant, is the first non-vanishing term. What's the potential? Oh, there it is. R hat over R squared dotted into the vector. Okay? Which is R hat dotted into the z direction QB over R squared. What is that as a function of the direction? Here I am, this is my position. Here I'm looking at the potential. X is R times R hat. What is R hat dotted into the z direction? In terms of some coordinates that we know. This is the polar angle theta, which is the direction relative to the z-axis. So what is R hat dot? I'll call it z hat because there's too many things, so many notations, so just get your act together. What is that? Cosine theta. So this is a characteristic polynomial, a function of theta. This function of theta is actually proportional to y10 of theta, the spherical harmonic. That's going to come back to us this whole week. In fact, it's also equal to, as was just described, the Legendre polynomial. So it's related to the Legendre polynomial. This shape of the potential has two poles. It's a dipole, right? This is a dipolar, right? If I were to write the equipotential surfaces here, it would have a positive and negative as a function of theta, because cosine goes from +1 to -1, right? So the shapes of the distribution depend on what the moments are. They have characteristic equipotential surfaces that represent the multipoles. All right, very good. Now I want to come back to how I started, the more formal way of writing this. So we can write down a general expression using the spirit of irreducible tensors. Buckle up, people. I'll just get us started. Okay.
Find my seatbelt.
So, let me get my notes here so I can get all the factors right.
Alright, we'll get to multiple expansion of an arbitrary field.
We're going to write the most generic expression for any charge distribution, and therefore what the potential is for those different multipoles, and thus what the field is. All right. So what we said a moment ago, where this was equal to, in this case, that's the formal expression. So this is then equal to, if I write this as a power series, the sum over coefficients, which I'll call L, because that's what this should be called, 1 over L factorial, minus x prime, divided into the gradient, 1 over R, to the power L. And this is equal to x prime I, x prime, del, the partial derivative with respect to the i's coordinate. So what this then is equal to, if I write out the first few terms, I get the 0th order term minus the first term. And then the second term is going to be 1 over 2 factorial, which is 2. And then I'm going to have two sums, so I'm going to use two dummy variables. Plus dot, dot, dot. Okay? And the term, the most general term, is going to look like this. I'm going to have this to the power L, so I'm going to have, this goes I1, I2, dot, 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 I the elf guy, and then the partial respect to the first guy, the partial respect to the second guy, the partial respect to the elf guy. That's what I've done there, is just taken this and written it out L times with L different dummy variables. This dummy variable, that dummy variable, etc. Okay? So this is a general power series solution to how the Greens function. And so what I see is, this is some monomial or polynomial. I'll call this is a tensor, which is the outer product of x prime with itself, L times. And this is another tensor. I'll call it T. And then we contract, we sum over I1, we sum over I2, we sum over I3, and sum over all that, and that's some number. Okay? Let's take a quick look at this before we quit for the day. Let's look at the second order case. Firstly, this is symmetric, because it doesn't matter the order in which I take the derivative. Moreover, what is its trace? Well, I set the two indices equal, that's the diagonal elements, and I sum, which is the Laplacian, which is what?
For a point charge.
That's the Laplacian of 1 of R. It's 0. I mean, it would be a delta function if I was at the origin, but I'm far away from the origin. So this is 0, because R doesn't equal 0. Remember, otherwise it's a 3D delta function. So what can you tell me about this tensor? It's traceless and symmetric, and thus it's irreducible. It's irreducible. Now, everyone remembers problem 2, or maybe it was 3, of problem 1, where we had the contraction of two tensors. One was irreducible, right? So if I look at this guy, this is this tensor, and this is this tensor, which I'm contracting. But this guy is irreducible, which means only the irreducible piece of this contributes when I contract them together. So I'll call that the irreducible part of this. This is already irreducible, so I don't need to bother, but I'll just do it. What the heck? And what is that? That's equal to xi minus xj minus a third delta ij r squared. That's the irreducible piece of this, because I've subtracted off its trace, which I can also write as a third 3xi xj minus r squared delta ij. Oh, look, that was something that looks familiar, over like we saw in some other part. This form is the irreducible piece of that. In fact, let's conclude by just doing this. Let's take this derivative and then take that derivative. Remember, this is the derivative with respect to xi of r, right? Which is the square root of x squared plus minus y squared plus z squared. So if I do that, this guy is equal to minus xi, I'm sorry, over r cubed. And so this whole thing is equal to 3xi xj minus delta ij over times what we have, this partial derivative gives us again the irreducible tensors. There is an intimate relationship that we're going to explore next time between irreducible tensors, solutions to Laplace's equation, and spherical harmonics. This is going to be a little bit crazy, but those connections are extremely important. If we want to understand the whole geometric structure of multipole moments, we need to understand the connection between irreducible tensors, the solutions to harmonic equation, which is the Laplace equation, and spherical harmonics. So I recommend, before Thursday, reading lecture note 6, and then go from there. All right? Very good. All right. Have a good rest of your day.
Yes. Are you in quorum too? Make sure no one steals my stuff, I gotta do something real quick.
The same time that we do like,